So in the previous video, we covered the switch statement and switch expression, the evolution from the traditional colon syntax with all fall through to the clean arrow syntax with exhaustiveness checking. Okay, so in this video we go deeper into pattern matching in switch, which is one of the most powerful features introduced in Java 21 and one of the most heavily tested on the OCP exam. So when you want to write code that behave differently based on the type of an object, you have two ways. So if you see the slide here, you have two pieces of code. On top, the old way, so manual, check and cast. Okay, this approach uses type pattern matching introduced in Java 16, but it still feels repetitive because it relies on an if-else chain. Okay, so if obj instance of circle, the check, Java verifies if obj is actually a circle here. So circle C is equal to circle within bracket obj. So it's the cast. The cast, even though you just check the type, you still have to manually declare a new variable C and cast obj to circle to access its methods. Okay, and then we have return math.py into c.r within bracket into c.r within bracket. So it's the logic, right? So you finally perform the calculation. Then we have else if, then within bracket obj instance of rectangle is the repetition. You repeat the exact same ritual for every possible shape. Okay, the problem is the compiler does not know if you have covered all shapes. If you add a triangle class later and forget to update this logic, the code might just fall through or return a default value without warning you. Okay, so at the bottom we have another piece of code, that's the new way. So pattern matching for switch. So this syntax collapses the check, cast and logic into a single elegant line. So return switch within bracket s, instead of just switching on integers or strings, Java now lets you switch on objects. We have to understand that carefully. Okay, so switch s, right? So here it's an object, s is an object. So then we have case circle C arrow math.py into c.r into c.r. So this does three things at once. Okay, so test if s is a circle and then casts s to circle automatically and binds it to the variable c, which is immediately available for the calculation on the right side of the arrow. Okay, so and then we have case rectangle r arrow r.w into r.h. Okay, it's the same logic, clean, readable and no redundant type names. Okay, so one line part type, the check and cast happen in a single pattern, and if you are switching on a CIL type, the compiler verifies you covered every possible case. So this is pattern matching in switch, and it changes how you think about conditional logic in Java. In this video we are covering three things. First, type patterns, where case itself tests the type and binds the variable. Second, guarded patterns using the when keyword, where you add an additional boolean condition to a type pattern. And third is sealed interfaces and records as the natural companions to pattern matching, enabling exhaustive switches with no default required. Okay, by the end of this video, you'll understand how all three work together and be ready for every pattern matching question on the OCP exam. Okay, so welcome back to the Java OCP 21 series. I am Arup Basu from ClusterMicro Technologies. Let's move to the next slide. So this slide brings together three of the most significant modern Java features: sealed interfaces, records and pattern matching in switch expression. All three were finalized in Java 17 and Java 21, and all three appeared together on the ACP 21 exam because they are designed to work as a system. So sealed interface shape permits circle, rectangle. Okay, the sealed keyword on the interface declaration means this interface has a fixed closed set of permitted implementation. The permit clause lists them explicitly, circle and rectangle. No other class anywhere in the code base can implement shape. Not in another package, not in a subclass, not in a future library. The list is final and enforced by the compiler. This is a fundamental shift from traditional Java interfaces, which are completely open. Anyone can implement them. Sealed interfaces are deliberately closed. The benefit is that the compiler now has complete knowledge of all possible subtypes of shape, and it can use that knowledge to verify exhaustiveness in switch expressions, which we will see in a moment. Okay, then in line 2 we have record circle double R implements shape. So circle is a record. So record was created to reduce boilerplate code that developers usually write for classes that only store data like DTOs, value objects, etc. Right? So it is a simple syntax that instead of writing a full class with private final fields, constructor, getters, equals, hash code, toString, etc., you just write public record circle $R, right? That's it. One line does everything. So what happens behind the scenes? So when I write record circle $R, the compiler does a lot of work for me. So we have a field, right? A private final field R is created. So the data is immutable by default. You cannot change it later. Then a constructor is automatically generated. It takes $R and assigns it to the field. Then a method R is created. Mind it that it is R. It is not get R. Okay. So this is the key difference from traditional Java beans. And then equals, hash code, toString, all standard methods are generated automatically. So records work perfectly in collections and debugging with extra code. So why this matters is that there is no need to write boilerplate code manually. Okay, it's cleaner, more readable, and less error prone. Encourages immutable design. Okay, which is safer in concurrent systems. Then if you see that in traditional class, lots of code for simple data, but in record, it is one line and everything is generated. If your class is just holding data, use a record is the modern Java way, okay? Then we have circle implements shape. It is one of the two permitted implementations declared in the sealed interface. This is fine. A record can implement a sealed interface as long as it is listed in the permits clause. And then we have record rectangle WH implements shape. Okay, it's the same pattern. Rectangle is a record with two components, width W and height H. So it also implements shape. Together, circle and rectangle are the complete and exhaustive set of possible shape implementations. The compiler knows this and nobody else can implement shape. So the set of all possible shape objects at runtime is exactly either a circle or a rectangle, nothing else, okay? Let's move to the next slide. Pattern matching in switch. So we have this code here, static double area shape S, then return switch S, case circle C, math.py into C.R, then C.R, then case rectangle R, R.W into R.H. So this example shows pattern matching inside a switch expression, one of the most powerful modern Java features. Switch S in Java 21, switch expressions can switch on object types, not just integers, strings and enums. Okay, this is pattern matching in switch. Then we have case circle C, math.py into C.R, C.R. So this is a type pattern. The pattern circle C does two things simultaneously. First, it tests whether S is an instance of circle. If S is a circle object, this case matches. Okay, and second, it binds the matched object to the new variable C, automatically casting it. So C is now typed as circle within the right hand side of this case. So once we have C as circle, we can call C.R to get the radius, the auto-generated record getter. Then we compute pi times r squared for the area of a circle. So note that no explicit instance of check here, right? No explicit cast to circle. The pattern does both in one clean expression, okay? And then there is no default case. Notice that there is no default case here. Okay, in traditional switch, omitting default on a switch expression would be a compile error because the compiler cannot verify all cases are covered. But here the compiler knows that shape is sealed with exactly two permitted implementations, circle and rectangle. So no default is needed and the compiler accepts it without error. So this is the power of sealed plus pattern matching combination. So if you add a third permitted type to the sealed interface letter, say triangle, and do not add a corresponding case to the switch, the compiler immediately gives you an error in the area method. Okay, you cannot miss a type. Okay, so the compiler will enforce the completeness. Let's move to the next slide. Now let us look at the method classify. So this example extends pattern matching with an additional feature, guarded patterns using when. It lets us add extra conditions on top of type matching. So we take an object and classify it based on both its type and value. Switch expression returns a string. So this is both type checking and value computation in one step. So first line is case integer I when I less than 0 then arrow negative ints. Okay, so this is a guarded pattern. It has two parts. First, the type pattern, okay, integer I, so matches if O is an integer and binds it to I, and second, the guard when I less than 0, when, right? So this matches only negative integers. Okay, so both conditions must be satisfied. The object must be an integer and the integer value must be less than 0. If both are true, the result is negative int. The when keyword was introduced in Java 21. When acts like an inline filter after type matching. Okay, pattern must match first, then condition is evaluated, and if condition fails, Java moves to the next case. Okay, and then in the second line we have case integer I arrow. This catches the remaining integers. Because the previous guarded case already handled negatives, this effectively means non-negative integers. And in third line we have case string arrow string then s. Okay, so matches if O is a string, then binds it to s and concatenates it to the label. The pattern extracts the actual string value for use in the result. Okay, and in the fourth line default other. Okay, default then arrow other. So since we are switching on object which is not sealed, there are infinitely many types that O could be. Okay, we cannot list them all. So default is required here to handle everything else: long, double, custom classes, arrays, anything that is not an integer or string. The order of cases in pattern matching switch is also very significant. So more specific cases must come before the least specific cases. If you reverse these two integer cases, that case integer I, then arrow non-negative int, then case integer I when I less than 0 negative int. So then the next line, second line, case integer I when I less than 0 negative int would be unreachable, right? So compiler would reject this. The second case can never be reached because the first case already catches all integers including negative ones. So this is a compiler error. This case level is dominated by a preceding case level. Okay, so thanks for your time. See you in the next video.